Here is my solar inverter, an Aurora. It had failed with error 031. I have repaired it by changing the relays using the YouTube video by Andy Reynolds to show me how to do it. It's now working fine. I was able to resolve the problem by changing the relays. However, I thought, why have the relays failed? So I decided to do an investigation. I opened up a relay, and much to my surprise, I found that the heating effect that had destroyed the inverter had not come from the contacts of the relay, but from an internal current path which I think was generating a lot of heat. The contacts were not burned, but the pin which had showed heating was close to the hinge of the relay. So I have set up an experiment to look into where the heat comes from. If we now look at my experimental setup, here we have a variable transformer where I can set up a variable voltage which goes into a transformer. The transformer has a special winding that I have put on which will give me very little voltage but a high current. The relay I have connected, soldered onto the moving part of the relay which has been folded up, and the normal contact, the normal pin of the relay for connecting to the printed circuit board. I've also soldered on a thermocouple which is connected to a temperature meter. I measure the current in the winding of the transformer with a clamp-on sensor from a British Gas energy monitor, which is connected to an oscilloscope. The oscilloscope will show me the peak-to-peak value of the signal from the transformer. I have also, to calibrate, set up a calibration curve where I connected my avometer into the circuit, so that by measuring the amps on the avometer and correlating against the peak-to-peak voltage on the oscilloscope, which are these figures here, I was able, using Excel, to construct a calibration graph which gave me an equation for the millivolts to amps. This was then extrapolated from, in steps of 2.5 amps up to 65 amps, what millivolts I would get for each of these amp settings. So now we're ready to start the experiment. Here is my temperature meter, and I can select either the sensor on the relay and free air so that I can measure the ambient. It's getting warmer. It's risen by 2 degrees centigrade since I came into my attic here. And if I set my onto this probe here, you can see when I warm that up, it goes up. So this is measuring ambient on number 2 and the actual temperature of the relay on number 3. So the relay at the moment is ambient. This has been disturbed by me touching it. So we've got ambient now at 9 degrees centigrade. We're on the B scale of the instrument, which is this scale here. Scale B, set by the switch down here. I'm now going to start with 10 amps. So I'm closing the circuit breaker and looking at 10 amps should be 939 millivolts. I'm now adjusting to 939 millivolts. Or as near as I can. There's 960 millivolts, which is just over 10 amps. And the temperature is rising. It's now at 12 degrees centigrade. So I'm going to give it a few minutes. The temperature is now 13 degrees centigrade on the relay and 9.7 degrees centigrade on the free air. I'm now going to increase to 20 amps. 20 amps is a voltage of 1.839. .84. I can read the peak-to-peak voltage on the oscilloscope here. That's saying 1.84 at the moment. And the temperature is rising. I'm going to take a break now for the temperature to stabilize. Right, we've left that for a while now, and we have a temperature on the relay of 23.5 degrees and a temperature free air of 10 degrees. I'm now going to increase to 30 amps, which is the highest rating of that relay according to its specification. So 30 amps, we're looking for 2.739. .76. So now 2.76 2.76 or thereabouts. And the temperature is going up again. We'll let it stabilize again. Right, the temperature is now stabilized, and we have 58 degrees on the relay, and on the ambient we have 10 degrees. I'm now going to take it up to 40 amps. To do that, I'm going to have to change the scale on the temperature meter, which is now showing me close on 60 on this scale. And I'm going to 40 amps, which is 3.64 volts on the oscilloscope. And I may need to change the scale on the, no, 3.62, 3.67. Okay, that's about as close as it will get. I'm now going to move the display very slightly so that it's a bit more centered. It has stabilized at 99 degrees centigrade. And if I compare the ambient, go onto the B scale and go to channel 2, we have 10.5 degrees centigrade. So that's where I'm going to stop. I'm going to turn the current down now to 0 and open the breaker. This is an unrealistic situation. The relay is able to radiate freely, but in the original configuration, the relay would not be able to get rid of its heat quite so effectively. I'm now going to set up this relay energized and put the current through the 2 contact terminals. I will not be measuring ambient this time. What I will be measuring is the temperature at the 2 contact terminals. So I'm going to have a break now while I set this up. I've now set up the new system. Here is the relay. There's a diode across it to prevent a backsplat, and the temperature probe is on the hot pin of the relay. The relay is energized by a power supply, which is giving it 11.17 volts at 85 milliamps. That means approximately 1 watt. So, not surprisingly, we have some heat in the coil even at 0 current. The heat from the coil is warming the relay. The contact pin is at 25.5 degrees centigrade, and near 26 degrees centigrade. I'm now going to start putting some current. So variac to 0, close the circuit breaker. I know it's not really a circuit breaker, it's something else. And going to the calibration curve, we're going to start at 10 amps, which is 0.939 volts. (900 millivolts, 940). Control from the variac isn't particularly precise. And the temperature is going up. We're going to take a break here while it stabilizes. We're now at 10 amps for a while, and it's stabilized at 39 degrees centigrade on the B scale, and the ambient is 11.2 degrees centigrade. I'm going to take the current up now to 20 amps. From the calibration curve, that's 1.839 volts. .86 is about as close as I can get. And the temperature is now rising again. I'm going to have to change the scale onto the C scale. And I'm going to give it time to stabilize. We're at 76 degrees now on the temperature meter, and that is at 20 amps. To be honest, I'm surprised it's not higher. But this is the measurement. So 76 degrees on the relay pin, and the ambient going to scale 2, and B is 11.2 degrees. Going back onto the relay pin. I'm going to take it to 30 amps now. That is the maximum that the relay is specified at, and that is 2.739 volts. .74. So the temperature is going up again. It's now above 100 degrees C. It's 110 degrees C. Give it some time to stabilize. So we're now at 134 degrees centigrade on the pin with an ambient of 11.2. I'm now going to do the last increase up to 40 amps. 40 amps, we're 3.64 volts on the oscilloscope. 3.64. Something interesting happened there. The current has gone down to 0. Okay, stop the car. The current went down to 0 as I was increasing, and I was wondering why, and then I looked at the relay. And this pin has desoldered. That happened at round about, let's see, we were at 30 amps before. Around about 35 amps. That was an interesting experiment. I'm surprised at how little the temperature had risen. The initial measurements on the opened up relay showed that the heat is being generated in the internal parts of the relay, basically here. And that's where it's the narrowest cross section for the current. So, in conclusion, I think I've proved where the heat is coming from. I'm surprised I didn't get quite as much heat as I was expecting, but it's interesting that the solder joint on the relay did melt, but at a much higher current than one would expect in the inverter. The inverter is a 3.6 kilowatt inverter. The output voltage will take us nominally 240, which means nominally 15 amps on the relay, which should be well within its specification. So unless there's something going on that I don't understand, I don't know why the relays are, or why the inverters are failing with heat from the relays. But they are. Thank you.